A culture of bacteria obeys the law of uninhibited growth. If 500 bacteria are present initially and there are 800 after 1 hour, how many will be present after 5 hours? So for this problem, because it says that the bacteria culture is following this law of uninhibited growth, we know that this population is growing exponentially. Remember, the law of uninhibited growth is telling us that there's nothing that's keeping the population from continuing to grow. So we have unlimited space, unlimited resources. So exponential growth will happen, and it'll look graphically something like this. So there are two ways to attack the problem once we decide that we have an exponential growth problem. So one way is to go ahead and use our general exponential model, which is a is equal to a sub 0 e raised to the r times t power. And remember, that's exactly the same as the formula that we sometimes refer to as PERT, the PERT formula, which is the money that we generally talk about, the formula we generally talk about when we're dealing with money that is compounded continuously. Okay, but since we're talking about population here, we reassign the variables. So rather than calling P the initial amount, our principal amount, we call it our A sub 0 amount. But it's important to realize that these really are the same exact equation, the same exact model. So I'm going to start off showing how we can determine the answer to this problem using our exponential model here. So I would begin by organizing the information in the problem in a table. So remember that A sub 0 is going to be our initial population, so that's going to be a constant. And then R, which is the growth rate constant, or the relative growth rate, that's also going to be a value that we're going to be able to solve for. So the two unknowns in this problem, the quantities that are changing, are time, the amount of time that is gone by, and then the amount of bacteria in this case. So because we're measuring in hours, we'll let T equal the number of hours that this experiment has been taking place. And then A, our population in this case, is the amount of bacteria. So now let's reread the problem and see if we can identify what we've been given and organize it in the table. It says 500 bacteria are present initially. So that would be at time 0, we have an amount of 500 bacteria. And there are 800 bacteria after 1 hour. And then the question is asking us how many will be present after 5 hours. So when t is equal to 5, we're interested in this question mark, our amount. So let's begin with our initial amount. We know at time 0 we have 500 bacteria. So that's going to give us our A sub 0. So we can start off with A is equal to 500 e raised to the r times t power. Moving on, we have another ordered pair here. When time is 1, the amount is 800. So thinking of this as an x and a y value, in this case a t and an a value, then we can just substitute these values in. Our amount is 800 bacteria. And that's when our time, our t value, is 1. So substituting those values into our model or our equation gives us this equation to solve. And we're going to be able to solve this equation for r. So we'll want to divide both sides by 500. So 800 divided by 500 simplifies to 8/5. Of course, if you'd rather deal with a decimal, that would be fine as well. If you want to write 1.6 here, that would be fine. You just want to make sure that you go ahead and leave this in exact form. We would not want to round the decimal here because we'll lose accuracy. So either you leave it as an exact fraction or an exact decimal. And now this is an equation that is in exponential form. So to get it out of exponential form, we're going to do a rewrite, and we'll rewrite it in log form. And our logarithm will have a base of e. So this is going to be log base e of 8/5 is equal to r times 1. But log base e is the same as natural log. So I'm actually going to save myself a little room here and just replace this with the natural log of 8/5 is equal to r times 1. And of course, we really don't need the times 1, so we can say that r is equal to the natural log of 8/5. which if you input that in your calculator, if you're curious what kind of a decimal that is, you'll see that R is approximately 0.47. So it's important to notice that R is a positive value. That makes sense because the bacteria population is growing in this case. And we're not going to use 0.47 for our future computations. It is important that you either use the natural log of 8/5, the exact form, or you can go ahead and use the store feature on your calculator, and you can store the natural log of 8/5 if you wanted to. Either way. So this now is going to give us our model. So the model, or the equation that models the relationship between the time and the number of bacteria, in this scenario, is A is equal to 500 e to the approximately 0.47 times t. And again, just making note that we're not going to actually use the 0.47, but rather we'll use our stored amount, or we'll go ahead and use the exact value of natural log of 8/5 for that value. So now back to our table, we would like to know how many bacteria there are after 5 hours. In other words, we're interested in A of 5. A of 5. So you can substitute that in your calculator. I encourage you definitely to try that now with these videos so that you can be sure that you're not making any careless calculation or calculator errors, I should say. And pause the video if you need to, but checking your calculator against this answer, it looks like we'll have 5,242.88, and that would be the number of bacteria after 5 hours. Now I know you cannot have a portion of a bacteria, or rather we can't measure that, but I do like you to go ahead and include the decimals, specifically 2 decimal places, so that way you can check the accuracy of your calculation, making sure that you did not round early in the problem, but that you only rounded once. So that's one way to attack this problem, using this model of A is equal to A sub 0 e raised to the RT. Now there's a second way of tackling exponential growth functions, and that is by determining the multiplier. So again, I would organize the information from the problem in a table, knowing that at time 0 we had 500 bacteria, and 1 hour later we had 800. So exponential growth, as well as decay, is characterized by multiplication here as we go from one y value to the next. So we should be repeatedly multiplying by a constant value. In other words, on this problem, we have a value of 500, and the question is, what would we multiply that by? So let's say 500 times what number will give me the next y value, or the next a value, which is 800. So 500 times what is 800? Well, you can see if we divide by 500 and simplify, then we're multiplying by 8/5. 500 times 8/5 will give me the next value of 800. And if we wanted to then continue that, we certainly could. If we wanted to know, okay, how many do we have? Then after 2 hours, well, we would multiply again. We would take 800 and we would multiply it by 8/5, which will give us 1,280 bacteria. So if we're asked to find how many we have after 5 hours, we certainly could just continue multiplying repeatedly by 8/5 until we eventually got to t equals 5. But that's not going to be a very efficient method, especially if the problem asks you for a much larger value of time. So let's look at how we can create a model knowing now what the multiplier is. And the key is to remember that whatever that multiplier is, it's going to become the base in your exponential model. So we'll still start with the initial amount of 500, just like we did before. But now the base here, this is going to be 8/5. So the difference is, in our previous model, we were using a base of e. And so instead of using a base of e here, we're using a base of 8/5. So it's just going to be another way to model this growth. So we'll have 500 times 8/5. Now the 8/5 is what you're multiplying by repeatedly, so that's going to be 8/5 raised to the t power. then I always recommend that we actually check this to see if it works. So let's take one of our ordered pairs. So how about 1, 800? In other words, 500 times 8/5 raised to the first power better give us an output here of 800. So certainly you go 500 times 8/5. If we go ahead and do our division, will end up being 100 times 8. So you can see, yes, this does work. It gives us the appropriate number of bacteria after 1 hour. So this is an alternative model. This would certainly work as our model. Now let me go back to our first way of doing this just so that you can compare the two. When we did this earlier using this exponential model, we ended up with the equation A was equal to 500 e to the 0.47 times t power. But remember, 0.47 really was the natural log of 8/5. So I just want to show you that these two equations actually are the same if we had natural log of 8/5 times t. So let me clean this up and give myself a little more room so I can demonstrate why these are actually going to be equivalent equations, equivalent models. So if we have A is equal to 500, e raised to the natural log of 8/5 times t power, you can see that we have multiplication here in the exponent. So that would allow us to rewrite this as 500, the quantity e to the natural log of 8/5 power, all raised to the t power. Because remember, when we have a power raised to another power, we're going to multiply the exponents. But then this e raised to the natural log of 8/5 simplifies because we have a base of e and the natural log is also a base of e. So that's going to simplify. They are inverses of one another, and it'll simplify to just plain old 8/5. And that's why we do end up with 500 times 8/5 to the t power. So it turns out that this new model that we've written here with a base of 8/5, it actually is equivalent to the model that we used earlier when we used a base of e. And that's why you can do this problem either way. So by choosing the multiplier, or figuring out our multiplier here of 8/5, we avoid all of that work that we did earlier to find r, since this problem didn't specifically ask for the growth rate. And now we just want to know how many bacteria there are after 5 hours. So you'll be inputting 500 times 8/5 raised to the 5th power, which hopefully makes sense to you, because if we go back to our work in the table, we were saying that we would repetitively multiply by 8/5 over and over and over again here until we eventually got to the time value that we wanted. So you could see, okay, we would look for a time of 3 and we'd have to multiply by 8/5 again. And if we do another time, 1 hour later of 4, we'd multiply by 8/5 again. So it should make sense that if we wanted to go all the way here to a t equals 5, that we would have to then multiply by 8/5 5 times. And that will still give us our answer of 5,242.88 bacteria.